First dive into the topic of similar polygons. So we've spent a whole bunch of time up to this point talking about whenever polygons are congruent to each other, but now we're going to start looking at this new idea, which is that two polygons can be similar. And so the question is, what does it actually mean to be similar? Because, just in our normal speaking, similar can mean a lot of things. Things are alike in some way or some shape or form. And so in geometry, of course, we have a very specific definition for what it means to be similar. And here's what that definition is. So two similar polygons, there are polygons whose corresponding angle measures are congruent and whose corresponding side lengths are proportional. And so I think that's probably best explained with an example. So let's go ahead and draw something out here. So let's say I've got a polygon here. It's a pretty good polygon. There's one. And then I can have another polygon that's similar to it. So not exactly the same. It's not necessarily the same size, but it has all the same kind of features. And so I'm going to make one that's just a little bit bigger. And it looks like it has all the same attributes. So if I lined up these angles, maybe I should name these as well. So this is A, B, C, and D. And this is, I don't know if I got the right color, E, F, G, and H. I should have done that in the right order. Let's start over. E, F, G, and H. It'll be the case that these things are similar to each other if all the corresponding angles are congruent. So if A is congruent to E, and B is congruent to F, and C is congruent to G, and then D is congruent to H. All right, so if all the corresponding angles are congruent, and then all the corresponding side lengths are proportional. So there's several different things that we can write out here. So the first thing I should probably start with is what we call a similarity statement. So my similarity statement, just like a congruence statement, kind of tells us what the two objects are that are similar to each other, and the order in which we write them is really important here. So if I say A, B, C, D, if I call that my first polygon, then I have to say that it's similar to, and so I'm using, it's like my congruent symbol, but it's just the twiddle, is similar to, and then I have to match with the corresponding parts, A to E, and then B to F, and then C to G, and then I have D to H. So this is my similarity statement, where I'm writing out the two polygons that are similar to each other, and all their corresponding parts line up. So that's number one. Number two, then, we have their congruent parts is another thing that we can list out. Congruent parts, which in just this case is just the angle. So angle A is congruent to angle E, and angle B is congruent to angle F, and angle C is congruent to angle G, and angle D is congruent to angle H. And then I have one more thing, which alludes to this second part here, whose corresponding side lengths are proportional. I have what's called my statement of proportionality. Proportionality. There we go. So my statement of proportionality is, well, a proportion. It's going to be a set of ratios that are all going to be equal to each other. And so let's say that I tell you that this quadrilateral is just, this is 4 times as big. It grew to be 4 times the size as the previous one. So what that means is if I took the length of AB over its corresponding side EF, okay, that ratio in this case should be 1 to 4, because this is 4 times as big. And so that'll be the case for all of these, all my corresponding parts, B to C over F to G. And then, let's see, C to D to G to H. C to D, G to H. And then my last part, A to D and E to H. So this is my statement of proportionality here that tells me the corresponding side lengths are all going to be not congruent to each other, but proportional to each other. So my corresponding angles are congruent, but my corresponding side lengths are proportional. And so I can tell you right now that one of the big mistakes people are going to make is that they're just going to tell me that all the corresponding parts are proportional, but that's not the case. We know that if I have a quadrilateral, that the sum of the interior angles has to be 360 degrees, and the sum of the interior angles over here has to be 360 degrees as well. And so it can't be the case that these angles are 4 times as large, because that would make a new quadrilateral where the sum of the interior angles are 1,440 degrees, which is not the case. We know that it's 360. So all the corresponding angles are congruent, and all the corresponding side lengths are proportional. So I have my similarity statement, I have my congruent parts, and I have my statement of proportionality. And so the statement of proportionality, this ratio of the sides, we actually have a name for, and it's right here. It is the scale factor. So the scale factor is the ratio of the lengths of 2 corresponding sides of 2 similar polygons. And what we're actually going to find out is our scale factor is so much more than just the ratio between the side lengths. It's actually the ratio between any of the linear measurements in these 2 polygons. So for example, if I drew in a diagonal, let's say I draw in a diagonal from A to C, and then also from E to G, then these would have the same ratio. So wherever that scale factor is, will also be the same as A over C, so that diagonal over, and then E to G. Okay, any of the linear measurements of my 2 polygons. And on top of that, what is also a linear measurement, but the perimeter. So the perimeter of A, B, C, D over the perimeter of E, F, G, H will be the same. Did I put this in the right order? Yeah, let's see the same scale factor here. So any linear measurement between the 2 polygons, if they are similar, will have the same proportionality. So for triangles, we can talk about, of course, all the other unique segments I have in there. I can talk about angle bisectors or perpendicular bisectors, or altitudes or medians, or any of the things in there. Their corresponding parts in the other triangle will have that same ratio. And so I really emphasize, though, the fact this is just for the linear measurements, because it'll not be the case that the areas have the same ratio. Okay, the areas would be this squared measurement, so it's not linear anymore, it's squared or quadratic. And so it will not have the same ratio, but there is a relationship there that we'll figure out later. So similar polygons are just 2 polygons whose corresponding angle measurements are congruent and whose corresponding side lengths are proportional. And more than that, not just their side lengths, but any linear measurements. Any linear measurements are proportional to each other. That includes diagonals, that includes medians, that includes altitudes, that includes perimeter as well. And this ratio that I keep talking about, we also call that the scale factor. So it's a scale factor of the 2 similar polygons. So that's what similar polygons are. We have this very specific definition for them. And so we're going to apply that to be able to find a whole bunch of different measurements, and later on we'll even try to prove that 2 polygons are similar.